we should be good to go. I hope you're all doing well. Had a good weekend. So just so everyone knows, I'm feeling a little sick, and since I know what that means, and today, no, I don't think I have the coronavirus. I'm just having some really bad headaches and stuff. So I might have to cut it a little short. Being on computers is sort of aggravating a little bit. So we'll see how it goes. But yeah, hopefully at least we'll be able to go a pretty good chunk of the way through with everything we need to do. Also, just so everyone knows, I'm really behind on grading and lots of other things for that matter. So yeah, I'm sorry that the grades are a little behind. I'm going to try to get caught up with them, but everything is taking quite a bit longer to do. So we'll try to get caught up with things as quickly as I can. Does anyone have any questions or business kind of concerns or anything of that sort? All right. Then let's pick up a little bit where we left off last class period. Someone's saying in the chat, and I could not agree more, it's really hard to do this shit under current conditions. Thumbs up. Completely agree with you. Yeah, the times are indeed a bit challenging for some of the more abstract pursuits, perhaps. But well, it's hard to do the abstract stuff when the concrete stuff seems unstable. I hope at least, that as best as possible anyway, we can struggle through it. I mean, I know you all have shit going on that's far above and beyond the stuff going on with this class. I've got students who are homeless. I've got students who are having to find the random open coffee shop somewhere to try to connect the thing. So believe me, I know everything that's going on with you all. The best I can say is that we're going to try to struggle through as best as we can. And if you're having a hard time, get in touch with me. We'll find some way to sort of arrange stuff. Figure out how to do things, how to fit things into people's schedules, how to fit things in with the kind of constraints people have. So yeah, this is a rough time for all of us, and for many of us, a far rougher time. So don't hesitate if you are struggling, and this is all for all of you in asynchronous land too. Right? For people who are struggling, having a hard time getting in, please don't hesitate to get in touch with me. If you're having a hard time getting stuff to work, I'm going to do whatever is necessary to try to arrange things for people to succeed in this class as best as possible, given the various kinds of constraints and circumstances that we're all facing. So, yeah, hang in there, do your best, and contact me when your best isn't working, and we'll figure out some other alternatives. Any other sort of initial comments, thoughts, questions before we try to resume a little bit? And you have one less paper to worry about too, at least. So that's probably a decent thing for everyone. No other initial thoughts? All right. Then let's pick up a little bit where we left off. And let's at least, since we're here, right? Fun, philosophy. Hey, why not? An hour, why? Why not? Why not consider some weird questions and some abstract stuff? And what the heck, right? All right, so we're doing Schrodinger's account of life. And the reason why we're doing it, amongst other things, is just because I think it's really cool. I've never really heard anyone say the kind of thing that Schrodinger is saying in this essay. It's like a lot of the stuff, the Mayer stuff and the Badal stuff, it has novelty and interests, don't get me wrong, but things very similar to what Mayer was saying about these teleonomic properties were said by the ancient philosophers, and Mayer says as much. I've never really read anything like Schrodinger. This analysis that Schrodinger is offering of what it means to be alive is just really different, really novel, and has some really interesting and cool implications. So we sort of the background last time. We'll review the background first. Today we're going to get into the cool upshot of all the hard physics background. So, okay, let's do it. What's the hard physics background we had to start with? Okay, so according to Schrodinger, and again, it's important to remember, Schrodinger is himself a physicist, right? Indeed, he is one of the founders of quantum mechanics. Schrodinger's cat, if you've ever heard of that, you've heard of Schrodinger. All right. So Schrodinger's claim is that the laws of physics and chemistry, as they're ordinarily considered, will not be able to explain what happens in space and time within a living organism. This isn't vitalism. It's not because somehow living things violate the laws of physics. It's because physics just hasn't studied the kind of thing that a life form is, and so therefore doesn't have anything special to offer on the subject yet. So why not? Why are the laws of physics and chemistry as ordinarily considered not going to be good enough? Well, Schrodinger says it's because these laws are fundamentally statistical in nature. Okay, so what do we mean by that? We did a whole big discussion of this last time, so I'm not going to go through everything, but at least to review the big picture upshot. Due to the effects of quantum mechanics, heat motion, in effect, the behavior of individual molecules is effectively random. I mean, it's not completely random, but at the very least, there's going to be random fluctuations within it that are random in principle, not random just because humans don't understand it well enough. Quantum effects are random in principle. And so if you look at an individual molecule, I'll go back to the main screen for a second. So let's say this is an individual molecule, and you'd expect it to just sort of fly across the screen like that. It's probably not going to do it because it's going to get bumped, bopped, prodded, pushed all over the place. And so it's just going to be moving in a highly irregular way. And this is true for sort of every molecule. Molecules, as a result of quantum heat motion, move in really irregular ways. They don't demonstrate ordered behaviors amongst themselves. But so in a law of physics, for example, the second law of thermodynamics that we're going to talk about, right? That law says that closed systems increase their entropy over time. That's not a true descriptor of any individual atom. That's a description of the statistical aggregate of what those atoms will all do put together. Right? And as Schrodinger argued, you actually need a lot of atoms for the laws of physics to really hold well universally. Right? It took 1 million molecules to have less than 1% error. And that's not very good, right? So he actually thought you need billions, if not trillions of atoms to have the laws of physics even approximate what we would normally think of as sort of a mechanistic law, right? A law that just is universally followed in every single case. Okay. So what do we have in the case of normal physics? We've got disorder, molecular disorder, as a result of quantum mechanics, that if you add enough molecules in, eventually starts to demonstrate ordered behavior. So you have disorder producing order. Right? And how does it do this? It does this statistically. Right? It's the key claim that these laws are all just statistical in nature. Just if you average out the motions of all of the molecules, and you have enough molecules, and you take the average of enough molecules, you'll get the result you'd expect. That's okay. So let's just pause for a second. Any questions about that? Anything anyone wants to go over, review, question about that?
Hey, Professor.
Go ahead.
This is Yannick Bourne. I had a question regarding that. Is that similar to the concept of randomness, like the philosophical randomness? I think I'm not. Is that similar to that? I know if you know what I'm talking about. I don't have the exact name of it, but it's like the theory that all things occur in a sense of randomness.
Yeah, the swerve, the sort of Epicurean swerve or whatever. That kind of idea.
That thing.
Yeah, it's a little bit similar. But so it's a little bit similar if you look at the really small levels. Let me actually bring up the video that I sort of showed everyone last class for a second. Give me just 1 second to find this. Let's look at that video of Brownian motion again that we looked at last class. Here we go. This is not quite the same video, but it's similar enough. So let me broadcast it to you all. The frame rate could chug a little bit, so I apologize that the frame rate's a little chuggy. All right. So this is basically this video. What it's showing us, and hopefully you're all seeing it. What this video is showing us is a really zoomed in view, not even of individual atoms because we can't zoom in that far, but of bits of pollen just floating in water. And what you should be seeing is how all of these individual pollen molecules, they're just moving chaotically. Right, their movement seems to be random for all intents and purposes. So on that level, if we zoom in really close, yeah, what we see is largely random movement, like you're sort of suggesting, right? But what Schrodinger's saying, if you zoom out, so when we zoom in, it all looks random. When we zoom out, what we see is that seeming randomness, that really is random in a sense, there are certain sort of statistical trends that we can identify within it. Right? So for example, if you look at an individual molecule as it's falling, right, as a result of Newton's law of gravitation, what does Newton say? The molecule should just do this. Right? Just go straight down. If you actually look, that's not what it's going to do. The molecule is going to go, right? But there's an overall trend and trend line of it moving downward. So it doesn't move directly downward as if everything was just purely mechanistic, but there's a trend to move down. And if you have a lot of atoms and you measure all of those trends, eventually you get something that sort of looks like what Newton's law of gravitation actually says. So individually, molecules move randomly. Collectively, they actually show ordered behavior. And that's what the laws of physics are supposed to be sort of capturing. To say that they're statistical is to say that if you get enough of them and you look at enough of them all at once, you discover that what's really was random individually collectively produces ordered behavior. So was that helpful? Does that sort of help answer your question?
Yeah, that makes sense.
Okay, good. The thing that's different about life, Schrodinger says, is that it actually acts mechanistically, not statistically, or at least it's way closer to mechanistic behavior than statistical behavior. So let's go back to the screen. This is still just doing the review stuff from the last class. So if you look at living things, what we discover is a single molecule. He calls it a macromolecule or an aperiodic crystal. Right? We would now call this DNA or RNA. He's predicting what DNA and RNA had to look like 10 years before they were actually discovered. What we discover is these special molecules, these molecules that are involved with hereditary behavior, the passing on of genes, and also the regulation within individual cells. They are indeed molecules. A DNA is a single molecule. It's composed of 100 atoms or so, something like that. Not that many. Right? But this molecule, so one molecule, based on what we were saying before, that one molecule should behave completely random if it's like all the other molecules we studied. But the DNA molecule doesn't behave that way. Not only is it highly stable internally, right? It can even be hit by an X-ray, for example, and mutate, but still survive, not explode, still survive as a result of the mutation. So it's stable internally. It also contains within itself an ordered program, right? And think here the Mayer stuff, all that stuff that Mayer was talking about. I think the DNA molecule for Mayer is the explanation of the program. Right? This ordered program that then governs the entire cell and through the cell, the entire rest of the body in an incredibly mechanistic and ordered way just from one single molecule. One individual molecule, this DNA molecule, produces order just by itself. And he thinks that's just nothing like the other molecules we look at, right? All the other molecules, because of the randomness of heat motion, right? They individually are disordered. You only get order when you look at a lot of them. The DNA molecule starts off as ordered, and it produces from its order an ordered system. And this is just not the kind of behavior of molecules that physics and chemistry had studied. Right? And so that's why he suggests that physics and chemistry, as they're ordinarily considered, can't explain what happens within space and time within the organism. Right? The kind of outcomes or the results of the one DNA molecule are just radically different from the outcomes and results produced by a single, say, hydrogen atom. They just have radically different results. Since physics and chemistry, as normally conceived of, haven't studied this kind of molecule, it has nothing to offer biologists in telling them how the molecule will behave. Right? Whereas organic chemistry, he says, which does study things that are at least similar, have some useful things to say. And so that's sort of the basis of the divergence here for Schrodinger. That's the basis of the DNA molecule just has these unprecedented effects that the physicists would never have been able to have predicted just by looking at other kinds of molecules. Other molecules just don't work the same way the DNA molecule works. And so the normal kinds of accounts physicists and chemists give is not going to be adequate to explain what this special hereditary molecule does, right? What we would now call DNA. So all of that's just a little bit of review. So that was what we were doing last class. Again, let's just slow it down. Any questions, any thoughts, any comments? Anyone have anything you want to do just on what we covered with that sort of first part of the Schrodinger reading? All right, we're good so far. All right, let's now turn to then the interesting upshot of this. Okay, so what is it actually then that the DNA molecule does or causes? That's so weird. Why are living things so weird? What's different about us? What's the oddity? So let's just do some, if I was Mayer, the oddity is teleonomic behavior. Right? These sort of behaviors that can only be explained teleologically. To Mayer, that was the odd thing. That was the weirdness. To Bedau, coming from Mayer, right? What's odd is how many of these teleonomic behaviors there are. And he says the evolutionary explanations that you would need to give for them. For him, that was what was so weird or different. Schrodinger is going to give a completely different answer. He's not going to actually care about the behaviors themselves. I mean, he points to them. Or their diversity. Again, the diversity maybe is interesting and cool too, but that's not the fundamental thing. The thing that's interesting, bizarre, weird to Schrodinger is the result of these teleonomic behaviors. And what is the result? So let's give the big picture answer. What is the result? Living systems keep doing their thing. We want this to be as broad as possible, right? So they do their thing way longer than non-living systems do their things. It's the length of time. It's that you don't die after, I don't know, 10 seconds, say. Because I could actually throw some chemicals in a vat and have those chemicals do some pretty interesting things, but they'll finish doing their interesting things really quickly. 10 seconds or so, they'll be done. What's really interesting about you is because, what are you? You're a giant vat of chemicals, like, right? I mean, you are literally a flesh bag, right? That contain, you're literally a bag of flesh containing a boatload of chemicals. And those chemicals, they keep doing their thing. They keep catalyzing for, if everything goes well for you, what, 80, 90 years? That's unprecedented. That's not normal. And again, it's not like because you're a star, right? Like, if you were a star, sure, it takes, billions upon billions of years for the star to just burn through all of its material just because of how huge stars are. But I could make a human-sized vat of chemicals and get it to start catalyzing, and it'll finish in 10 seconds still, right? It's not how many atoms you have that make you different or that cause you to keep doing you longer. Something about the kind of chemical reaction you're engaged in continues to do its thing for way longer than we'd expect. And so someone's asking, how long do we need, right? Like would 4 years, would that be long enough? Sure, I mean, he's not talking about any precise amount of time. It's just that you do what you do longer than the physicists would expect, considering you just as a giant bag of chemicals. Right? So if you're like a giant bag of chemicals, you keep having weird chemical reactions way longer than normal. And why? Why are you able to do that? Because you breathe, because you eat, because you drink, because you poop, because you pee, right? Because you metabolize. All of these teleonomic behaviors, they all boil down to a kind of metabolism for Schrodinger.
Oh, Professor?
Yep, go ahead.
I was curious. I guess I was a little confused. So what's the difference between the metabolizing aspect of the human being and then, what's so unique about us and then let's say, the sustenance of a star? That's the one point I was confused on.
Yep. So what we're going to say, and we'll need to do this, this is what we're going to try to figure out the whole rest of the day is almost that distinction, in fact. So you're going in exactly the right direction. I'm going to need to do a lot of explanation to explain what I mean by this, but here's the rough answer. The star is constantly increasing its entropic value, and you are not. In fact, you decrease your entropic level. Now, okay, what's entropy? That's where we're going. But entropy is a physical property of things Stars always increase, and everything like stars, basically all inanimate things, basically just ever escalatingly increase their entropy, and you don't. And that's the difference. So the star just takes a really, really long time to attain what's called heat death, right? If we were just looking at the atoms in your body, it would not take those atoms very long to attain heat death, but because they're metabolizing, it takes way longer than you'd expect. So okay. That's probably not enough, I'm guessing, but hopefully it's at least the framework of the answer, and then we'll fill out that framework.
Yeah, okay, that makes sense. Yeah, it was, that kind of gives us a base to work with.
Exactly. Yeah, that's the framework, and then we'll try to fill that in the rest of the day, because yeah, you should not necessarily know what any of that meant yet. Right? There's still plenty to figure out, and I got some more YouTube videos to show you to awesome. Perhaps be helpful.
Cool. Sounds good.
All right. All right, so let's start trying to break this down. Let's talk about the second law of thermodynamics for a second. Right. I'm going to show you a video, right? Because actually, it's really hard to actually explain the second law of thermodynamics, but actually, you all know it when you see it. So I'm going to show you something, and I want you to imagine you are actually seeing it take place before your eyes. Right, so you're actually seeing this in front of you. Try to figure out why you would get really freaked out and possibly think you were going mad. All right, I hope everyone saw that. If you actually were just sat down at a table and that happened, you would think you were nuts. You would think you were losing your mind, right? Or that you were dreaming, or that someone had drugged you. Okay, so why? Why isn't it a problem at all if you saw someone drop a wine glass and the wine glass broke? You're like, oh, that's fine. But if you saw the wine glass spontaneously regenerate itself, you would think you were going mad. What's the difference? Why is it different in reverse?
That's not the process we're used to, and seeing how things kind of break down.
Yeah, that's not how it works, right? You almost didn't even know how to say more than well, that's not how it goes. Go ahead, Angelina, you're unmuted.
Yeah, so I was gonna say, yeah, the second law of thermodynamics, it says that everything's going towards disorder, and it never comes back. So we can see a lot of it in daily life, but we don't think about it. But since the opposite would make us think about it, and that's why it would be weird.
Exactly. It would. I mean, what you just saw, the reason why it looks so impossible, the reason why you would think you were going mad if you ever saw it, is because that's the second law of thermodynamics.
Yeah.
That's actually what we just demonstrated. Why that reverse video never will actually happen. That's the second law of thermodynamics. What we're used to is ordered systems collapsing into disorder. We never see the opposite. We never see a disordered system becoming more ordered, except when we're looking at a living thing. And it's not going to violate the second law of thermodynamics, so we'll need to make that clear too. But that's the only exception. There's lots of videos I could find of this. If you've ever seen a video of a wall collapsing, again, the wall's not going to spontaneously reform itself. There's a one-way order. The second law of thermodynamics frequently gets called the arrow of time. There's actually a forward in time direction, and it's one where things become increasingly disordered. So let's try to define the second law of thermodynamics and keep that video in mind to help. Okay, so according to the second law of thermodynamics, a closed system, and we'll need to define that later. So a closed system, and again, we'll have to define what I mean by that, but a closed system necessarily increases its disorder over time. and it will never become more ordered over time. Or I had someone in the chat ask me about entropy. Let me just define entropy real fast. Okay, I'm not actually going to do it, but here's the actual physical definition of entropy is really confusing. But basically, just think of entropy as disorder. If you're increasing entropy, you're increasing the disorder. So we could also state the second law of thermodynamics in terms of entropy. Entropy always increases in a closed system. Never stays the same or decreases. And what would decreasing entropy mean? That would mean decreasing the disorder of the system. Or the system gaining order. All right. So there's a question in the chat about entropy. I hope that helped with just a straight up definition of what I mean by entropy. And Do Androids Dream of Electronic Sheep? So hopefully you've all had a chance to read that by this point. Right? This was what that guy who lived in that apartment by himself, this is his concept of the kibble, right? The kibbleization of the world, right? The thing that's just spaces become more and more disordered over time, right? A metaphor you can use, and it's actually not even really exactly a metaphor, right? Like when you walk around in your room, why does your house get out of shape when you don't clean up after yourself, right? Because you touch things. I had to pick up the pen, and I could put it back where it goes, but I'll just put it there. It's fine. And then I put another thing there, not where it was at first, and before you know it, my house is chaos. Right? And it's just because of the same quantum heat motion is the reason why this is taking place. Heat motion will just constantly be disordering systems. And unless something fixes it, unless if I come around and clean my house, right, stuff's just going to be all over the place. Stuff's going to be in disorder. And this is the fundamental law of the universe. If any of you have heard of the idea of the heat death of the universe, the universe as a whole is a closed system. The inevitable destiny of the universe is to attain maximum entropy, maximum disorder, where things are so disordered that even protons no longer can exist at all. There's basically just a soup of quarks and black holes. And it's thought that should take about 1 trillion years or so to happen. Yep. And someone's saying that they talked about this in their biology class. Indeed you did, because of Schrodinger. That is indeed why you talked about this in your biology class. He was the first person to talk about living things in this way, at least in any sort of systematic or codified sense. So that's why this paper is so overwhelmingly important. Right. So how are people doing just with the basic idea of entropy? Is it well, an important thing to note here, I'm not actually gonna do this because I'm not actually a physicist and I don't even think I understand it well enough to actually explain it. This isn't some weird fuzzy notion. It's something that physicists can actually measure. What it actually is, it's like a measure of like the amount of heat it would take to return a system to its previous state. That's basically it. So I think the unit of it is something like calories per time squared or something. Like it's basically how much heat would you need to reset the system to its previous state? How much heat would have to be added to a system to do it? So this is indeed a measurable quantity. Schrodinger wants to really emphasize that. This isn't some fluffy concept of order that the philosophers talk about, that physicists don't talk about. No. This is a real physical measurable quantity, right? And so what we mean by entropy is quite firm to his mind. And so when we talk about the sun, right? So you go back to that example we brought up earlier. The sun, right? Yeah, it keeps engaging in nuclear fusion, and it will engage in nuclear fusion for billions upon billions of years. But if you were to actually measure the entropy of the sun, it would always be increasing. So all it's doing is it's just burning through its fuel, right? So the fuel of the sun is like hydrogen, and then that fuel gets burned and it becomes iron. And if you have enough iron, eventually that gets fused into, right? And then and then the sun explodes, and then the sun explodes, right? So the sun basically is sort of just constantly burning through its fuel, and once its fuel gets low enough, it will die, so to speak, quote unquote die, right? The sun will stop, that fusion activity will stop taking place. And that's inevitably going to happen unless someone shoots a death ray into the sun or something, right? Like unless you add in energy to the sun, the inevitable result of the kind of behavior that the sun is engaging in is that the sun will eventually burn itself out. Similarly, if I start a fire, right, on a stick, so let's say this was a stick for a second, I light it on fire, which I'm not going to demonstrate because I don't want to burn down my basement, right? If I did do that, what's inevitably going to happen? The fire is going to transform the stick such that the stick can no longer burn. It burns up the stick, and then eventually the fire too will burn itself out. Right? That's increasing the entropy value of the stick. The stick becomes more and more disordered and can no longer do the interesting behavior that it was doing of being on fire. So how are people feeling with this idea of entropy? Do we have any questions, any thoughts, any comments about any of it so far? And again,
that makes sense.
That helps? Okay, good. And again, just remind yourself, why does this look so weird? And indeed, actually, statistically, it is actually possible that all those atoms in the glass will decide to just spontaneously reformulate, but the odds of it are so unbelievably small that it's effectively impossible. Right? The law of thermodynamics, too, is a statistical law. It's not a mechanistic one. Right? It's just that the odds of that number of atoms deciding to spontaneously go back to their original state is so infinitesimally small that it's, for all intents and purposes, impossible. All right. So how are we doing so far? So any questions right now? All right. If you're doing okay. Oh, we got a question here. So so someone's asking me, someone's being difficult. I'm just kidding. I'm not actually giving you a hard time about it. But someone's being difficult and actually asking me a real physics question about entropy and about the way that I'm distorting the concept of entropy by not describing it in terms of physics. Yes, technically you are correct. Entropy is the amount of ways that a closed system can change. And what's important is that those options are always decreasing, right? That amounts to what we're calling disorder. Because what disorder actually is sort of like is that the impossibility of entering certain kinds of arrangements anymore. So you're not wrong about that. It's sort of to translate the physics into sort of more normal terms, though. What it is to say that the system has a limited set of possible motions within it is that it's become more disordered. Right? An ordered system can just go in more places than a disordered one can. So I was just teasing you with I do not indeed mind the hard physics question, but yeah, that's going to be the limit of my ability to answer the actual hard physics questions about entropy. All right, now let's talk about life and entropy. So we've been talking about entropy just really broadly. Now let's talk about it in terms of life and entropy. Or life in the second law of thermodynamics. Superficially, and this is wrong, but superficially, it looks like life forms violate the second law of thermodynamics. It actually doesn't, right? That would be vitalism if that was actually true, but it's not actually. But superficially, at least, it looks like it. Why? Because if you look at me, my entropy seems to be remaining the same. At least until I die. Okay. So look at me, I'm here, right? I am not indeed flying all the pieces. I'm not decomposing. All of the chemicals in my body are more or less staying where they're supposed to. Right? My cells aren't breaking down, or even the ones that do break down get replaced by new ones, even. Right? So if you actually just measured me, my entropic level is staying the same, and indeed, it might even be decreasing. For example, if I recover from the coronavirus. Well, let's even do cancer. Cancer is a better example. If I'm being ravaged by cancer, indeed my entropic level would be going up. But if I recover, what is cancer, right? Cancer is basically out of control, disordered cellular activity. So cancer is actually increasing the entropy in your body. That's why it's killing you, because basically death is entropy. If I get better, though, all of a sudden, all of that disorder within my body is gone. I've actually decreased my entropic level. Again, remember, it's a little bit counterintuitive. Decreasing entropy means increasing order. And increasing entropy means adding disorder, or adding chaos into the system. So I maintain or decrease my entropic levels. Another example of it, when I was a single cellular organism, so when I was born, the amount of order present within that system when it was a single cell organism is way less than the amount of order present in, I don't know, how many organisms how many cells does a child have? I don't even know. Let's say it's a million just to make it up. Then those million cells are in a far more lower entropic state than the single cell was. And this will happen until death, right? What is death? Death is attaining maximum entropy. When the organism just breaks down and loses all sense of order. When you can't actually maintain and what this in fact sort of amounts to in effect is everything getting sort of just weirdly dispersed. So when your body is decomposing, it is quite literally entropying, right? It is dispersing. All of those sort of individual sort of segregated cells are no longer segregated. Now all those chemicals are just floating around doing whatever random chemical things they do. And there's a lot of you, so it takes a while for your body to be fully decomposed. It smells quite nasty, right? But we would not be in any sense tempted to mistake that for you continuing to be alive, because the order that sort of constituted you is no longer present in any meaningful sense, right? You've attained this sort of idea of heat death, or just in general, sort of this idea of maximum entropy. All right, so how are we doing so far? Okay. Now, nothing can actually violate the second law of thermodynamics, so the way we're characterizing this must be wrong. And indeed it is wrong, because a living thing is not a closed system. It is what is called an open system. And all that means is that it's a system that gets energy from outside of itself. And not just energy, it also gets entropy. I've got bad news for all of you. You're all vampires. I'm sorry to be the bearer of bad news. You are what Schrodinger he doesn't actually call you a vampire, but I actually like it better, so I'm going to go with it. You are what he effectively calls a negative entropy vampire. You steal order from your environment to preserve your own order. But here's the sad thing. Here's the bad thing. The amount of order you're stealing is always less than the order you preserve. Oh, sorry, I said that backwards. The amount of order you steal is always greater than the amount of order you preserve. And that's why you're a vampire. You are, in net terms, decreasing the environment's, or sorry, let me say that better. You are increasing the environment's entropy at a far faster rate than you are maintaining your own. So you are ultimately disordering the environment. You are a net minus to the universe. Thought of entropically, you are a net minus to the universe. You disorder the universe far more than you order yourself. And so let's do some examples. So someone is doing this in the chat, and let's just go with it. The example of stealing the entropy from a cow. Indeed, let's talk about it in somewhat graphic detail. So let's say you're not a vegetarian. Okay, what's one way you preserve your entropic levels? You eat a cow. What do you produce as a result of eating that cow? Poop. So what have you done? You took a cow, and look at a cow, right? We can go watch videos if you want, like highly ordered behavior, grazes, moves around, sustains itself, and what do you leave behind you? Poop. Great. Thanks. Net minus, right? And the amount of entropy in the universe has increased as a result of your action, and necessarily so. That's the sense in which you perfectly do violate, or perfectly do preserve the second law of thermodynamics, right? It's just the system then is like the Earth as a whole or the universe as a whole. That system is always gaining entropy, even if you, as sort of this like little isolated island within it, maintains your own entropic levels. Right? And so. Yeah, if you could actually, that's someone saying in the chat, this is exactly right. If you actually could steal more or preserve order at even the same rate as the order that you're taking, you would be functionally immortal. That's right. But yeah, it's just not possible. And you wouldn't even really be immortal because you still eventually would run out of entropy in the universe to steal. But yeah, you'd be at least incredibly long-lived. But yeah, that's not actually possible. It's always a net loss. You're not a perpetual motion machine. And you can also see someone suggesting this can be used to describe human climate change in a sense, but not necessarily, because the Earth itself isn't a closed system. So let's actually expand this a little bit. And why isn't the Earth a closed system? Because it's stealing entropy from the sun. The reason why we have for example, weather patterns that we have is entirely the result of the sun. Solar energy produced by the sun's fusion process heats up the Earth's atmosphere, and as a result causes all kinds of stuff to happen on the planet. It causes weather patterns to emerge. It feeds plants. That's why we all don't actually just haven't killed ourselves, because plants don't get their entropy from the Earth writ large. Plants get their negative entropy from the sun, photosynthesis. And so they've got not an eternal source, right? But they have a much longer lasting source of negative entropy that plants can leech off of, that then us animals can leech off of those plants. But again, even with the plant, the sun is becoming way, way more disordered than the plant is preserving its own order through photosynthesis. there's still entropy gain in the net system. And so in that regard, climate change itself, human climate change itself, you can maybe describe it in entropic terms, but it's not fundamentally it. Like, in fact, you can maybe even do the opposite. I mean, Schrodinger doesn't go here, but if you wanted to give the Gaia hypothesis, as we talked about earlier, sorry, hold on, tech problem, hold on. Again, remember the Gaia hypothesis is the hypothesis that the Earth itself is alive. You would do it on entropic grounds. You would do it by suggesting that the Earth as a whole effectively metabolizes, right? And that it's metabolizing sunlight in that regard. So one last question from the chat. So yeah, in principle, at least, other things besides us could have this property, and we'll talk about this a little bit later. So say maybe a special android or something. Sure, in principle, we could perhaps make one. Whether or not that makes us alive on Schrodinger's account, I'm going to suspend that to a little bit later. But yeah, at least in principle anyway, we could make other systems besides us have this sort of negative entropic value. But just note how different it is, right? So let's not do androids. Let's just do a really obvious example. So a car. Okay. So the car is able to run because it too preserves its entropy level to some extent. How does it do it? It does it by burning fossil fuels. But that's actually not enough. It also needs to do it by having humans maintain it. Because even if you just gave a car unlimited oil and just let it run as much as it wanted, it would eventually break down. Why? Because it's not just losing heat from its fuel source, it's also suffering internal damage to its system as a result of the heat exchanges that are taking place. Right? So I'm not a car guy, but like the engine is wearing down too. It's not just a fuel question. The engine is also starting to break down as a result of the activity. That's also an entropic increase, the damage done to the engine. So the car only maintains its entropic level, one, if we add fuel, but even more than that, if we go in there and fix it. We have to manually fix cars. Cars don't fix themselves. Your body fixes itself. Your body is what's we call an autocatalytic process. You maintain yourself. How do you do this? On the basis of the program that is DNA. That's how all this ties, how we're going to tie all this back together. The reason why you are an entropy anomaly is because of that DNA molecule. That DNA molecule is itself anomalous, right? It doesn't do the sorts of things that normal molecules do. The ultimate result of the anomaly is that you have the ability to repair yourself so long as you can metabolize entropy out of your environment. Whereas even if you let the car have all the energy it wants, it's still gonna break down. It's not gonna be able to maintain itself in accordance with the DNA program. The DNA program allows our ordered behaviors to continue far longer than you would expect based on our chemical processes. Because what happens when we live, right? We're constantly killing cells. Cells are breaking down. Cells are dying. Organs are getting weakened. We get sick. Stuff is constantly happening to us, and we fix it. Well, I don't have to open something external doesn't have to fix it. The system fixes itself. And it fixes itself so long as it has access to the negative entropy it needs to metabolize. And again, that's all very abstract. We can make it really specific, right? Like, so long as your cells will regenerate, so long as you get the amount of protein you need, and the right kinds of protein you need, and the right enzymes within the protein. I mean, we could actually get really, really specific about this, how you actually metabolize. It's going to be very specific chemical processes that take place. But on the basis of those chemical processes, what you end up with is a living, self-maintaining system. One that's going to preserve itself just in an unprecedented way, in ways that no other system we study will maintain itself. So I got a chat question here. Couldn't we describe our engine as breaking down by the degradation of various parts within our body? Yes, you could, right? But the key thing is you repair it yourself. The chemical processes within your body, the same, not exactly, but at least like the same basic chemical processes that are causing those systems to break down also repair those systems too. And that's possible because of the way in which DNA generates this program that can do things like, for example, cause the cell to repair itself, cause the cell to repair damage that it undergoes. And we already saw this even just within the DNA molecule itself. That was the crazy thing about the DNA molecule. It can repair itself when it gets damaged. If I hit a normal crystal with an X-ray, the crystal will literally explode. If I hit the DNA molecule with an X-ray, what will it do? It will mutate. It will rip apart, but then reassemble itself. Put itself back together. That's what you do. You put yourselves back together. And you don't do it in isolation. You only do it because you metabolize, because you're able to steal this entropy from your environment, right? But you put yourself back together, starting from the DNA molecule all the way up. Until you can't, right? Until eventually, the second law of thermodynamics always wins in the end, right? Eventually, yeah, you're going to die. You're not going to be able, your body will just lose the ability to do this, but you're going to be able to fix yourself way longer than anything else can fix itself. And all life can do this. This is what Schrodinger is identifying as this distinctive characteristic of life, is that it keeps itself going way longer than the physicist could ever have predicted, just looking at it molecularly. Looking at the molecules themselves, the physicist would never have guessed, or looking at the chemicals themselves, the physicist and chemist never would have guessed this process would have kept metabolizing for as long as it's able to. And ultimately, it's because of the DNA molecule. So let's do the ultimate order, and then let's pause, do some questions. But this is the last little piece of the Schrodinger that we're going to worry about. So here's sort of the big picture summary. The DNA molecule allows the living organism to self-repair so long as they can steal the negative entropy from their environment. So again, it's not that they can do it in isolation, right? You need an environment to do it, right? And this process is metabolism. The DNA molecule itself displays highly ordered behaviors. And the DNA molecule then serves as the program that gives rise to systems that themselves display novel ordering behaviors. ordered from order. Order producing order. And according to Schrodinger, this is new. He's never seen, physicists have never seen anything like this before. Physicists have only seen disordered systems that become ordered when you look at enough of them, when you sort of zoom out large enough. The systems internally are disordered. Life forms, Schrodinger's arguing, are the opposites. Life is ordered if you look at it really, really small in a microscope. And then from that micro state, the macro state is also ordered and preserves its order in a way that you would not have anticipated. So someone's asking, is there a label to put on this sort of this quality? The language that tends to get used is autocatalyzing, but it's a little bit of a weird term. Let me keep moving things up. I don't think I spelled that word right. Yeah, it's an catalyzing. There we go. An autocatalyzing process is a chemical process that continues to catalyze on the basis of its own chemical composition. And at least in Schrodinger's time anyway, we were the only one. We were the only autocatalyzing chemical process. We'll challenge that as we sort of go, but at least in Schrodinger's time, this is the only autocatalyzing process that he's aware of. And it's because of the special properties of the DNA molecule that the system is able to be autocatalyzing. So I hope that answer helps with the label question. That's at least a label we could give to it anyway. So let's take a step back. How are we doing here? Is this making sense? Are you seeing? So far, yeah, go ahead, please.
I was saying, yeah. So could you compare the way Schrodinger looks at the scaliforms and the micro and the macro to kind of how Muir, I don't know if you've heard of an author named Muir, but he makes a scaliform. He makes a scaliforms for Aristotle, and that like the universe is structured in a certain right. pattern the way Aristotle did it.
Right.
You say that kind of compare.
Yeah. I'm not familiar with him directly, but here's at least the kind of difference anyway. So for Schrodinger, the levels, if you want to put it this way, the levels of reality that normally get displayed physically are you've got microscopic disorder that because of how much microscopic disorder you have and certain statistical trend lines within the disorder, you get macro order. So macro systems are ordered systems, micro systems are disordered systems. The difference that he's seeing here is that the micro system is itself ordered, the DNA molecule, and the macro system is also then ordered. And that doesn't really fit with either of the kind of accounts that sort of the Aristotelians are going to give. The Aristotelians are going to give an account where you get sort of like ever escalating order, the higher up you go, sort of the scale of being. And that's not really what's going on here, right? Like, it's not the case that the sun has a low, I mean, it's a weird way to put it. The sun's not more or less exactly disordered than me. If anything, the sun's probably more ordered than me. But what's weird about the sun is that it's losing its order over time. Whereas even though I have a lot less order within me than the sun has, I'm keeping my order. The sun's always losing its order, even if it's in a macro level more ordered than me. It's always has a downward trend. I stay flat until I die. Right? Or if anything, I'm sort of like a curve. I sort of like go up. I'm more ordered, keep my order, then I die suddenly. So does that help? Does that distinction?
Yeah, that makes sense.
It's not so much level. So the sort of Aristotelian account's going to be more and more order, just characterizing the order itself, and Schrodinger's more interesting in the change of order, how the level of order is changing over time. And living things, our novelty is our order basically doesn't change over time. That is our sort of our novelty. Right? And we do it ourselves. We don't do it in the way that I can do it with my car by having to go in there and clean my engine out. I quite literally clean my own engine out. And again, it's gross, it's poop, but like Poop is me cleaning my own engine out in a quite literal sense, right? Whereas the car is just not capable of doing that. So the car needs something to clean it out. All right. Let's now define life then. If we're doing okay for now, let's try to use this to come up with a definition of life. On Schrodinger's account, at least, life presupposes the DNA molecule. Or at least something like it. Maybe not this specific thing, maybe something similar to it. And the reason for this is because again, it's important to remember, DNA hasn't even been discovered yet, right? He's not doing this because of the discovery of DNA. Everything that he said about DNA is based simply on quantum mechanics. And this is a prediction. He's making a prediction here, right? The biologists tell us that living things have certain kind of properties, right? Stuff that Mayer was talking about, and the stuff that also molecular biologists were talking about in terms of what they were seeing within cells in terms of hereditary substances. DNA, or something very much like it, the aperiodic crystal that he talks about, is the only thing in quantum mechanics says can actually have the properties that biologists tell us they have. So maybe it won't be exactly DNA. Maybe we'll find a silicon-based version of the same idea. But it's going to have to be something like this, he thinks. So what do living things do? Living things are governed by a DNA program. Or again, something very much like it. To maintain their entropic, to auto-maintain or to self-maintain their entropic levels. And this is indeed, metabolism is itself something that the DNA molecule itself explains. The DNA molecule tells the organism how to metabolize. It tells it to metabolize, and it tells it how to metabolize, how to get this negative entropy out of the environment, and so therefore it maintains its own entropic level. So this is Schrodinger's definition. Living things are DNA-directed self-maintenance programs of metabolism. And how is this different? So let's talk a little bit. How is this different from some of the other people we've read? Right. So the Horta, we don't know what the Horta was. Right. We don't know its biology, but there's not any difficulty with imagining some sort of silicon-based DNA-like molecule. It's possible. So the Horta, sure, something like it would definitely count as life. Would Data? No, Data does not have DNA or anything like DNA, and so therefore Data is not like a life form. Would a digital thing? Digital things do have programs, but ultimately, we're gonna do this on Thursday in great depth. Ultimately, no, the kind of program the DNA has is not the same kind of program that a program can have. A program can't actually metabolize. A program can synthesize metabolizing, but it can't actually metabolize. For Schrodinger, all of this is a chemical process. It's not merely a function of the form of the organism, but the matter too. So that question Badal was asking, is it all form that determines life, or is it form plus matter? Badal argued it was ultimately just form that mattered. Schrodinger is arguing, no, form plus matter. You need the matter too. You need the form as well, but you actually need the specific chemical interactions. Right. And so in the chat, someone's asking, the defining element of life is the existence of a DNA-like element. That's right. Yeah. Something like, and again, it doesn't have to be specifically DNA. We can allow for all different kinds of chemical compositions of life, perhaps, right? But it is some kind of molecule like the DNA molecule that is capable of regulating the entropic processes of the organism. And it's different from just having a battery or getting power in that way, right? Data might well be a moral person, but Data or the androids, because it seems pretty obvious that do androids dream of electronic sheep, right? It's clear that Dick doesn't think the androids are alive. Again, he might think they're moral persons or something, but Dick very clearly does not think they're a life form. He thinks they're radically different than how living things are, right? And the difference would be DNA, right? And the way in which having DNA just causes systems to react differently, right? I mean, the account that he's giving of life is really kind of tragic. It's important to note here. And that's why I wanted to redo Android's Dream of Electronic Sheep in a certain sense. If you want to put this more poetically, but Schrodinger's fine with it if you want to put it this way. Life is the eternal, ultimately futile struggle against chaos. Put it poetically. And indeed, that's what Philip Dick is portraying into Android's Dream of Electronic Sheep, right? Like, what is that crazy religion? Right? The crazy religion is sort of the Sisyphean struggle of the man and keeps falling down, right? Like why? Because that's what life ultimately is. Life is the system that, against all odds, tries to maintain its own entropic level, tries to maintain its own order in the face of the ultimate and inevitable eventuality of its own death. What was the definitive characteristic of those androids? Why does Decker, what's the thing that most of all disturbs Decker about the androids? It's when they know they're going to die, when they know they're going to be shut down, and they just stop. That was the thing Decker found most disturbing about them. Right? Because it's his job is to reveal them and then kill them, quote unquote, right? That's his job. What he found most disturbing was that once the androids knew they were beaten, they just shut down. Once a living thing knows it's beaten, what is it going to do? Continue to fight till it dies. And you don't even have a choice, because that's what the DNA tells you to do. Right? And again, we could throw in some natural selection. Why does DNA tell you to do that? Because of evolution. But evolution just is the explanation of why life has this property of the eternal struggle. It's not the definitive characteristic of the struggle. Right? So Badal defined life in terms of evolution and the kinds of behaviors evolution generates. And yeah, he's fine with it, right? I mean, Schrodinger's like, yeah, sure, evolution's happening and all that. Like, that's great, and it explains why but the key thing for him is the result. And the result is this struggle. The struggle to not die. And my car doesn't struggle to not die. Only a living thing, Schrodinger thinks, only a living thing, and again, only something that has this DNA molecule could demonstrate that kind of struggle to stay alive. And not just show it in some abstract sense, But what's really important for him, show it chemically. In case you're scared that he is talking too poetically. No, no, no. We're talking about chemicals. We are talking about what the chemicals within your body do. And the chemical processes themselves fight to maintain themselves. That's this language that I gave of auto-catalyzing. They self-catalyze. I spelled that word wrong, though. Try that again. And so for him, this is just a description of the novel chemical thing that your body is doing that no other chemical systems engage within. How are we doing? Is this helping? Is this making sense? What are some questions? What are some thoughts? What are some comments people have? All right. Well, if everyone's more or less good at this point, this is where I wanted to end for the day. So let me put the screen up one more time in case anyone needs to write any of the last little stuff I wrote down. So this is what I sort of wanted us to get through today, and I think this is a pretty decent place to stop. We didn't actually get to throw in any of the Kaufman piece, but I didn't ask you to really read it that carefully anyway. So we'll talk a little bit about how this Schrodinger analysis could get applied in some novel circumstances. So what we'll do on Thursday, we're going to use this Schrodinger analysis and use it to describe 2 life candidates, right, in great depth. We're going to talk about sludge monsters, or slime monsters, and why actually slime monsters might actually be possible on Schrodinger's model. But digital life is not on Schrodinger's model. So we'll review, again, I'm not going to have you read the Kaufman, because the Kaufman is just really dense and hard to read, but I'll draw out some of the key ideas from that Kaufman article, and then I'll have a new article for you from Bowden, where she argues for why digital life actually could not possibly exist. And that's what we'll sort of start off with on Thursday. All right. So any last thoughts or questions or comments? All right. Thank you all very much. Hang in there. I know times are what they are, and it's not good, but hang in there as best if you can. And again, don't hesitate to let me know if there's anything I can do to help with the times being hard. Have a good one, and I will see you all on Thursday.